A star that has reached the end of its life and bursts in a bright flash of light is what is known as a supernova. Supernovae have the ability to briefly outshine entire galaxies and emit more energy in a single instant than the Sun does in its entire lifetime. Additionally, they are the universe's main supplier of heavy materials. Supernovae are the greatest explosion that occurs in space, according to NASA. Supernovae were noted by numerous cultures before the telescope was created in the 17th century. The oldest supernova known to science is RCW 86, discovered by Chinese astronomers in the year AD 185. According to NASA's records, this guest star was visible in the sky for 8 months. Chinese and Korean astronomers first noticed the Crab Nebula, possibly the most well-known supernova, and they noted it in their records in 1054. According to rock paintings discovered in Arizona and New Mexico, Native Americans may have also witnessed it. Those early astronomers could see the supernova that created the Crab Nebula during the day because it was so bright. Before the invention of the telescope, supernovae were also seen in the years 393, 1006, 1181, 1572, and 1604, the latter of which Tycho Brahe examined. The term nova was used by Brahe, who described his observations of the new star in his book De Nova Stella, opens in new tab. Walter Baade and Fritz Zwicky at Mount Wilson Observatory coined the phrase supernova for the first time in reference to an explosive event they saw in the Andromeda galaxy known as S Andromedae, also known as SN 1885A. The researchers proposed that supernovas are caused by the merger of normal stars with neutron stars. According to study by the European Space Agency, a supernova will typically happen once every 50 years in a galaxy the size of the Milky Way. According to the US, this indicates that a star erupts approximately every 10 seconds somewhere in the universe. Office of Energy. The local bubble, a 300 light-year-long, peanut-shaped gas bubble in the interstellar medium that surrounds our solar system, was produced by a cluster of supernovae about 10 million years ago. The precise manner of a star's demise is influenced by its mass. For instance, our Sun lacks sufficient mass to go supernova. With the right amount of mass, a star can burn out in a fiery explosion, though the news for Earth is still not good, because once the Sun runs out of its nuclear fuel, perhaps in a couple billion years, it will swell into a red giant that will likely vaporize our world, before gradually cooling into a white dwarf. One of two ways a star can go supernova is: Type 1 supernovas occur when a star gathers material from a close companion and a runaway nuclear reaction causes it to explode. When a star of Type 2 supernova runs out of nuclear fuel, it falls under the force of gravity. Let's start with the more dramatic Type 2 supernova. Like the Sun, it will eventually run out of hydrogen and then helium fuel at its core, but it will have enough mass and pressure to fuse carbon. Type 2 supernovas must be several times as massive as the Sun. Estimates range from 8 to 15 solar masses. Once the star's core exceeds a particular mass, referred to as the Chandrasekhar limit, it starts to implode. Next, successively heavier elements build up at the center, and the star produces onion-like layers of material, with materials becoming lighter toward the exterior of the star. These Type 2 supernovae are also referred to be core collapse supernovae because of this. Eventually, the implosion returns to the core and launches the star debris into space, resulting in the formation of the supernova. What's left is a neutron star, a city-sized object that is extremely dense and contains the mass of the Sun. The classification of Type 2 supernova subcategories is based on the light curves, which show how the light intensity varies over time. After the explosion, the brightness of Type 2L supernovae gradually dims, whereas the light of Type 2P supernovae remains stable for a longer time before fading. Both type spectra bear the hallmark of hydrogen. Astronomers believe that stars with masses between 20 and 30 times those of the Sun might not go supernova. Instead, they disintegrate into black holes. Type 1 supernovae are assumed to come from nearby white dwarf stars in a binary star system because they lack a signature of hydrogen in their light spectra. The white dwarf becomes increasingly compressed as the gas from the companion star builds up on it. Eventually, this runaway nuclear reaction inside the white dwarf causes a catastrophic supernova outburst. Because all Type Ia supernovae are believed to burn with equal brightness at their apex, astronomers use them as standard candles to estimate cosmic distances. Similar to Type II supernovae, Type Ib and Ic supernovae also experience core collapse, although they have mostly lost their outer hydrogen layer. A Type Ib supernova's dim, elusive companion star was found in 2014 by astronomers. The companion star was significantly fainter than the supernova, thus the search took 2 decades. Recent research has revealed that before exploding, supernovae vibrate like enormous speakers and generate an audible hum. For the first time, a supernova explosion was captured by scientists in 2008, opens a new tab. Astronomer Alicia Soderberg peered at her computer screen expecting to see the little shimmering smudge of a recently exploded supernova. But what she and her colleague actually observed was a peculiar, incredibly bright, 5-minute X-ray burst. They were the first astronomers to observe a star bursting, thanks to their observation. Further research revealed that the new supernova, designated SN 2008D, had certain peculiar characteristics. According to Paolo Mazzali, an Italian astrophysicist at the Padova Observatory and Max Planck Institute for Astrophysics, our observations and modeling show this to be a rather unusual event, to be better understood in terms of an object lying at the boundary between normal supernovae and gamma-ray bursts. All types of supernova, with the exception of Type Ia, are caused by stars that have passed this threshold, which can happen in very massive stars when nuclear fusion is no longer sufficient to support the core against its own gravity. A supernova could result from the star's outer layers being violently expelled during the collapse. However, the star may instead collapse into a black hole or neutron star with little radiated energy if the release of gravitational potential energy is insufficient. The source of energy that can sustain the optical supernova glow for months has long been a mystery. Without some energy input to maintain its heat, the ejecta gases would swiftly darken. Some have proposed the center pulsar's rotational energy as a potential source. Although the energy that propels each type of supernovae initially arrives quickly, the radioactive heating of the rapidly expanding ejecta that follows is what dominates the light curves. In the late 1960s, the strong radioactivity of the ejecta gases was first computed using reliable nucleosynthesis principles. It has now been proven that this calculation is accurate for the majority of supernovae. Direct monitoring of gamma-ray lines did not definitively identify the main radioactive nuclei until SN 1987A. It is now known from direct observation that those anticipated radioactive decays account for a sizable portion of the light curve, or graph of luminosity, as a function of time, following the occurrence of a Type II supernova, such as SN 1987A. Although optical photons are used in the luminous emission, the radioactive power received by the gases that are released is what keeps the residue hot enough to emit light. Gamma-ray photons, primarily with energies of 847 keV and 1238 keV, are produced by the radioactive decay of 56 Ni through its daughters 56 Co to 56 Fe. These photons are absorbed and dominate the heating and, consequently, the luminosity of the ejecta at intermediate times, several weeks, to late times, several months. The electromagnetic radiation that supernovae emit is essentially a side consequence, despite the fact that they are primarily known as luminous phenomena. The electromagnetic radiation released during the explosion is a very small portion of the total energy released, especially in the case of core collapse supernovae. The balance of energy production in the various kinds of supernovae differs significantly. The majority of the energy used in Type Ia white dwarf detonations is used to create heavy elements and to increase the kinetic energy of the ejecta. Core collapse supernovae are often less visible than Type Ia supernovae, although they emit a much greater amount of energy overall. In these kinds of supernovae, gravitational potential energy is transformed into kinetic energy that compresses and crushes the core, releasing electron neutrinos initially from dissolving nucleons and then all varieties of thermal neutrinos from the superheated neutron star core. The energy that about 1% of these neutrinos are thought to have deposited into the star's outer layers is thought to be enough to cause the ensuing disaster, but once again, the specifics are difficult for existing models to replicate. The lower peak visual luminosity of Type II supernovae is due to lower kinetic energies and nickel yields than Type Ia supernovae, but energy from the deionization of the many solar masses of remaining hydrogen can help to cause a much slower luminosity decline and the plateau phase that is observed in the majority of core collapse supernovae. That was for today. Thank you for staying with us. Don't forget to like our video and subscribe to our channel.